Now, what we will do is now we are going to see how this property is going to affect us. Actually, we are going to show that this is going to make the problem much simpler when we apply this. So what I will now do is I will write this Cn term a little bit more explicitly. And so let us see what's happening. So Cn, which is x1, w1, wl sub 1 minus 1 is equal to, I have the, now what I will do is I will try to write the portions which are not dependent on the z value. So I will have Lx1, this is not controllable anymore. What else is not controllable? I will have alpha 0 to infinity of L x1 plus w1 minus t phi of t dt. What is this? Well, this is the carrying and shortage cost that I'm going to pay this period, carrying and shortage cost that I'm going to pay next period, carrying and shortage cost that I'm going to pay 2 periods later. So this is going to be x1 plus w1 plus w2 minus t1 minus t2. Now I have phi of t1. Okay, I will write over here phi of t2 dt1 dt2. Now what is this? Starting with x1 currently, given the quantities that will arrive next period and the period after that, I am simply writing the holding and shortage cost function L in terms of the demands which is going to incur on the way. Note that this is going to continue until when? Until I hit L sub 1 minus 1. In other words, these are the costs which are not controllable. So I will have alpha to the power L sub 1 minus 1. So if the lead time is 5 periods, I won't be able to control my carrying and holding, my holding and backorder costs for the next 4 periods. So this is what I'm writing here. So this is going to be, then I will have L minus 1 integrals. Okay, you can imagine this. So I will have L of x1 plus w1, w2, wl1 minus 1 minus t1, tl1 minus 1. And then I have the remaining. I'm not going to write that. Okay, remaining means that I'm going to write all the density functions. So what is this L1 minus 1 integrals doing there? They are simply, I am simply integrating over L1 minus 1 demands. So if demands are identically distributed, then you're talking about a random variable, which is the sum of that. If individual demands were, for example, normal, then this whole thing would be normal. So I would replace this with one integral, actually. Now, but what is important here is that all the costs that I have written up to this point are the costs which are not controllable when I have n periods to go. Because these are the decisions that I have already given in the previous periods. They are going to come to the system in one way or another. And it is going to affect the cost, but I have nothing to do with those costs. But now I am going to have another term, which I will call f sub n, and I'm going to decide that. F sub n is going to be, of course, a function of x1, w1, wl sub 1 minus 1. Where now, with this property, I can replace c sub n with this f sub n, because this part is actually a constant when I'm giving the decision with respect to z in period n. I am only going to be concerned with the inventory position. And this is the inventory position. So this is what this property is telling me. If I didn't have this property, of course, what would happen? This function would still have a lot of arguments. Yes?
Don't we have to multiply the second integral with some alpha?
Oh, okay. This is alpha squared. Thank you. Thank you. Okay. So let me, instead of dot dot, let me at least write dt L1 minus 1. Okay. So this is the last term. Okay. So I didn't write, but you have the density functions and the dt's. Okay. So you can see that now instead of dealing with this problem, which is not very simple, I have a single argument problem which can be solved. Now, what is Fn? Okay, so now let me write Fn here on the other board. Yes?
Why are we using the same discount rate for all the periods?
Oh, okay. Well, of course you can use, but there is no indication. Remember, in engineering economy, I mean, there is always no indication of which discount rate to use. So what you do is you taking everything up to date, you have a certain discount rate, and you simply say that that will be the discount rate that I'm going to have for the future. That's the only information that you have. Especially the discount rate is much more difficult to come up with, because that is a function of a number of things, cost of capital and so on and so forth. So if you have a value today, it is going to stay constant. That's your best shot, probably. Okay. Now, of course, in our case, we can have different alphas, which might, of course, change the results a little bit. If you don't have the same alpha, this property is going to hold, of course, but I think at some point in the computations, we might have a problem. Now, let's now define what Fn is. Now, remember, Fn is now only a function of the inventory position. Now, what we are talking about when we are talking about Fn, we are now going to consider the minimization problem. Remember? What we did now with this trick is, after writing this property, we are going to transform the problem from the Cn space to the Fn space. So Fn should take the minimization part of the Cn, if you recall. Okay? So Fn is sort of the minimization problem. What we have is, in this minimization problem, we are going to give an order. This time, the way that we write is quite straightforward. This is the current inventory. Oops, I am going to simplify this. Excuse me. I wrote this way, but it should be Fn U in general. So this is your current inventory position. Now, if your current inventory position is U, you are going to order y minus u units so that you are going to bring the system up to a certain level which is called y. Okay? So this is the cost that you are going to pay, purchasing cost. And then you are going to affect the inventory carrying cost of which period? Okay, now if you do all these tricks, we know that we cannot affect the inventory carrying cost of the next period, or the period after that, or the period which is one less than the lead time. So the only period that we can affect, the first period that we can affect the lead time, the inventory carrying and shortage cost will be L1 periods ahead. So L1 periods ahead, then I'm going to have all these integrals. How many of them? L1 of them, actually, which is going to take into account the total demand that incurred during those L periods. So this is going to be L of Y. Now I know that I'm going to bring the system to Y, inventory position. So there will be demands that will be deduced from this Y, and eventually the inventory level that I am going to end up with is going to be y minus all those demands. And then I have here phi of t1, phi of tl1, and then dt1, d of l, dt of l1. So this is going to be the first cost that I'm going to affect, the first period that I'm going to affect the inventory carrying and shortage cost. And then what do I have? Then I'm going to make a decision, and I will affect the next period. And so I'm going to have Fn minus 1. What will be the argument of Fn minus 1? I bring my system to y, inventory position. Note that the arguments are inventory positions. So my argument in the end period was brought to y after the minimization. Now after one period, what would be my inventory position? Y minus t. And this is phi of t dt. So what I did is I converted the problem to this problem, where I only take into consideration the relevant costs. These costs actually are not relevant for me. Why? Because the decision has already been given and I cannot affect that. So I only consider the immediate decisions that is affecting me, which is the purchasing cost plus the inventory carrying and shortage cost that I'm going to pay L1 periods ahead. And then I'm sort of going into the future. This transformation is the key transformation. With this transformation, what you do is actually this functional form becomes sort of immune of the lead time. With the only difficulty is that here you have the lead time demand coming into picture. Okay? Now again, don't forget, this L term is such that you have another integral in the L term. Do you remember that? If your starting inventory is positive or negative, doesn't matter, you have another integral that you use in the L term in order to charge for the holding and backorder costs. Remember? So basically, it means that you are taking into account lead time. Then you have another period there, another integral. So the total amount of demand that you take into account when you are computing this term is L plus 1, L sub 1 plus 1 periods, which is the response time demand. If you recall from 375, so the period of uncertainty is the lead time plus the review time, which is 1 period. So that is the number of periods that you take into account. Okay. Now this is the typical transformation that we use when we have periodic review problems with lead times. Of course, this is much simpler form. Now this looks like, more or less looks like the news vendor problem. With the only difficulty is that now instead of having single period demand, we have demands coming from more periods. But we can always represent that as a demand function. So eventually what you have is you have a shortage and holding cost that you pay to a demand function, okay, plus the purchasing cost, plus future costs. Now this is much simpler form, of course. So what is the optimal quantity to purchase? Y star minus U is the optimal quantity to purchase. Okay. Now further results. These are still the results for the single installation problem. So further results. now we are sort of coming to the turf that we know much better. Usually, if you did not take any inventory theory course, okay, you wouldn't be seeing the periodic review model in this form. Okay? But if you took an inventory theory course, probably it is taught in those courses. But I don't think that we have offered a course like that in the last few years. Okay? But this is basically the classical inventory problem. Now, the second property. If C of z function is given by k plus C of z for z positive 0 otherwise, then and, okay, this is number one condition, and if the L function is convex, okay, so this is sort of the next thing. If this is convex, then the integral of L of u will be convex, because you are adding up convex functions. Okay? And then in that case, if these two conditions hold, then there exists two numbers which I'm going to call lowercase s sub n and uppercase s sub n, and where if x1 plus w1 plus wl sub 1 minus 1 is less than s sub n, this is the lowercase, order capital S sub n minus x1 plus w1 wl sub 1 minus 1. Otherwise, do not order. So then there exist numbers Sn such that, okay, we can write our ordering policy in terms of these two constants. This is the SS policy that we know. Okay? So how do we obtain this? We obtain this from this functional form. Okay? And basically this simply tells us that of course the S values are going to change every period when we have discounting. Okay? When do we have all of these S sub n values equal to each other? Either when alpha is equal to 1 and you have infinite horizon problem, then it will be stationary. Otherwise, you expect those Sn's, lowercase or uppercase, to change every period, depending on how many periods are left to the end. Of course, you don't want to take a lot of risk when you are approaching to the end. Your inventory levels are going to go down. Whereas in the beginning, you can sustain a little bit higher inventory levels because you still have a lot of periods to go. But if you are dealing with a finite horizon problem, depending on the ending conditions, of course, you expect to have some changes in your decision parameters. Okay, but the idea is that this is basically the rule when we have this kind of an purchasing cost. So what we do is actually the proof is not in this paper, of course, because this paper is related to multi-echelon. This is just summary of the single echelon problem. So simply the proof lies here. If you take these functional equations into account, take derivatives, so on and so forth, you're going to see that that will be the structure that you are going to obtain, which is beyond little bit beyond the contents that I want to have in this course, but in a graduate inventory level course, well, maybe a little bit advanced, not introductory, one would go over the proof of this fact. But now we are going to take it as granted, okay? So this is going to be an SS policy. Now what would happen if C of z is simply C times z? What will happen? You are probably familiar with the result. In other words, if we don't have economies of scale in ordering, then we are going to have we are going to have a number which I'm going to denote by x sub n bar is going to be the order up to level and so the ordering quantity will be the maximum of 0 or x bar n minus x1 plus w1 all the way to wl sub 1 minus 1. This is typical order up to policy. Okay, you order up to xn if the total inventory position is less than xn, you order the difference. If it is more, you don't order anything. Okay. Note that we don't dispose. This is the case where we see the disposal idea much more clearly. We don't dispose. So what happens is that we have, again, the optimal policy depending on the stage of the decision process that we are at. Okay? It is going to be a function of that. Okay. So this is the summary of the single echelon, single installation problem. Now, what is the assumption here? The assumption here, we don't have that picture anymore, is that our supplier has infinite supply and will be able to supply any quantity that we order. Okay, so this is the premise. There will be a lead time, but we will be supplied. Whereas now, when we go to the multi-echelon case, we are going to see that this is not going to be the reality. If the retailer orders the warehouse may not have sufficient quantity. So what will happen? What will happen in reality? Whatever the warehouse has will ship it, and the remaining amount is going to be back-ordered. Okay, so this is the way that it's going to go. Now we are going to show that, actually, in the multiple installation case, more or less, this is going to be the optimal solution. Okay, but we have to show it more formally, of course. Okay, any questions on this? Yes?
Why are we using SS policy in second property and not in third one?
Well, because I am simply using the notation of the paper. Now, if we had, now these numbers are not the same. Xn value, Xn bar value is not Sn or the lowercase sn. So in order to differentiate, he used another parameter to denote that policy.
Actually, we can take the Xn bar value as Sn.
No. But it's not the same thing. It's not going to yield the same result. Because this is something else. So that's the reason why he differentiated between the parameters. But if you're talking about the policy structure, of course, this is an SS policy and this is an S policy. Okay, that's the way we denote. But if you're talking about the same problem, these parameters are going to be different, of course.
I'm asking that is there a specific reason that we are using SS policy if our cost function is like that?
Okay. Now, these are properties of the optimal solution, which means that when you solve this problem optimally, the structure of the decision variables that you come up with is going to follow this structure. So SS policy in that respect is the optimal policy to apply in this environment. So it is not because we wanted to use SS. You can show that SS policy is the optimal policy. So that's the difference. Now, in general, in inventory systems, what you can do is, in a few cases, you can show that this is the best thing to do. In other cases, what you do is, you assume that I'm going to apply S policy or SS policy, but that does not necessarily mean that it is the best possible policy. But in this case, the properties are actually the properties of the optimal solution. The optimal solution is always going to follow an SS policy if this is the cost function. Otherwise, it will follow this type of a policy if it is a linear purchasing function. Linear purchasing cost. Okay. Now we can go back to the multi-echelon case now. Okay. So now let us see how we are going to use these results. I am not going to be as elaborate in the multi-echelon case because notation and so on becomes much harder. I'll try to be very simplistic as possible, because we will be on the user side of this model. We are not going to prove that this is sort of the optimal solution, but we have to understand what's going on. Now, for simplicity, the multi-echelon case. So we just started to talk about the contribution of Clark and Scarf. This was sort of the introductory part that would lead us to the results. Okay, so for simplicity, we are going to take n equal to 2. So I'm going to assume that we have only 2 installations. Okay, well, this is what they did as well. And I'm also going to assume that L2 is 1 and L1 is equal to 2. So I'm going to use some specific lead time values, just not to complicate things a lot. Okay? Of course, the results are very general. So let us draw the picture. So this is installation 2. This is installation 1. The demand is from installation 1 only. This is the lead time that we have. This is the lead time from the supplier to the second installation. And we are going to assume that supplier has infinite capacity. So there is no possibility of additional delays here, but we might have delays here in case that installation 2 doesn't have the stock that we ordered. So L2, L1. Again, as I said, the demand is only in installation 1 in the version that we are going to derive, but it is not going to be a problem in general. We are assuming that C, the purchasing cost in 1 is linear. Purchasing cost in 2 has a fixed cost. So remember, we had 2 different types of cost functions. So this is the purchasing cost function for installation 2, and this is the purchasing cost function for installation 1. The logic is very simple. We usually think that the closest location to the supplier is a factory. So you have setups and so on and so forth. So if you really want to obtain economies of scale is important here. Whereas here, you are only shipping some items, so cost is more or less linear. This is, of course, a simplifying assumption. It simplifies the structure. In general, we are going to assume that only this installation is going to have this cost structure. The rest is going to have the linear cost structure, just to simplify things. Otherwise, there won't be any neat policy which is defined. Okay. Now, we are going to charge inventory holding and backorder costs in installation 1, because this is the location that sees the customer. Now, what are the costs that are charged in installation 2? Well, we are going to charge inventory carrying cost, of course, but we cannot charge for a backorder cost because we are not selling it to a customer. We are only making a delay within the system, which might affect the customer or not, we don't know. But if it affects the customer, we are charging it here. So we are not going to have any explicit backorder cost which we charge here. It doesn't make much sense. But that's not crucial. But still, this is what we are going to do. And we are going to assume that all excess demand is backlogged. So it means that we are going to satisfy that later on. So these are the basic assumptions. Now, one other thing that we are going to use will be the echelon holding cost concept. Now, anybody who heard about this echelon holding costs? Okay. Now, the concept is very simple. Now, let's now consider the following. This is installation 2. And what is holding cost in general? Holding cost is a certain proportion of the unit cost. So in stage 2, we are going to have a certain, let's say here, we are going to have a certain holding cost. Let's call it H1. And here, we are going to have a holding cost, let's call it H2. Now, what do you expect in general? Do you expect H2 to be greater than H1? Probably not. Why? Because basically, every time that we go from this stage to the next stage, we are making more expenses on the item. So the item cost is increasing. For example, this is sort of the automobile that comes out of the manufacturing. You have a certain cost. Then you carry that item to the dealer. Okay, so it means that there is a cost which is added at the top of that. So in general, we would expect H1 to be greater than H2. So this is actually what we expect in general. So what this means is as follows. Instead of making use of H1 and H2, we can use the so-called echelon cost concept, which is as follows. Now, I am going to define, for this example, I am going to charge here the holding cost, which is identical to H2 minus H1. What is that? That is the holding cost associated with the value added when you go from 2 to 1. Now, why do I do this? The reason is very simple. This is using the following logic. I mean, in total, I will be charging the same thing. But the way that I'm going to charge will be different. Okay? The logic is very simple. Instead of keeping inventory here, you could have kept the inventory in the factory. So that this differential wouldn't occur. So echelon holding cost is simply the holding cost that you add on every time that you change the stage of production. So from here, actually, if I rewrite this little bit, so the way that I'm going to charge will be the following. So I have 2 and I have 1. I am going to use H2 minus H1 as the echelon holding cost for installation 1. And what am I going to do for the other? Well, for the other, what I will do is I will consider all the stock which is here and beyond that point. And I'm going to call this as the echelon stock of installation 2, which is actually the stock which is here plus in the downward installations. So in this case, if we have n is equal to 2, this corresponds to the system stock. So I'm going to charge H1 to the system stock. So this is basically, if I repeat this, we have only 2 installations in this case. So echelon 2, installation number 1, is going to see all the inventory in the system as its own echelon inventory, and will charge H1 per unit. Okay? Now, echelon, installation number 1 is only going to see the inventory, the physical inventory that she has, and will charge H2 minus H1 to the inventory. Now, in total, the inventory which is charged is exactly the same. Okay? There is no gaming in that. Now, why do we do this? Because, as we are going to see, this concept is very much useful because how do you give decisions here in installation 2? You are going to give an order and make manufacturing. You look at the system. You try to find out the total amount of stock which is available in the system. Let's say that you have a lot of inventory in the retailer. This is going to affect your decision. So you are going to base your decision on the so-called echelon stock. Okay? Not only the stock that you have. I mean, can you imagine that, like, if you are a company which you are pushing all the inventory to the retailers, and if you don't look at the retailer inventory and make decisions of production, what will happen? The item is not going to sell and you will be pushing all the item to the retailer. So basically, an economic decision is going to be based on the so-called echelon stock. So what we are doing here is we are playing this little trick which is going to be very important in solving this problem. It's exactly the same thing, but we are accounting it in a little bit different way. The total is still the same. So we define echelon stock as the stock on hand plus all the stocks on hand plus on transit in lower installations or lower echelons. So echelon stock for the first installation is the stock in itself. Echelon stock for this installation is the stock in 2, plus the stock in transit in between, plus the stock in 1. Okay? Okay, let's make a very simple computation. Let's say that we have x1 here, x2 here. The original values, the inventory holding cost that you would charge would be h1, x1, plus h2, x2. No. This is basically the original holding costs. Now, by using, this is sort of the traditional way. By using echelon stock concept, the quantity is x1 plus x2, and we are going to charge h1 to that, okay? Plus h2 minus h1 will be charged to x2, okay? So the total is exactly the same.
In the first part,
yes.
The holding cost of 2 is h2.
Okay.
The holding cost of
Okay.
x1.
Okay. Now h1 is the holding cost in 1. It's not the echelon holding cost, but it's the holding cost. Okay. H1 is the holding cost here, H2 is the holding cost here. So the total holding cost that you are going to charge would be H1 X1 plus H2 X2. No problem with this. This is the traditional way.
I'm complicated because x1 belongs.
Okay, don't look at this picture. This is what I'm describing. This is the traditional amount that you are going to charge. You have X1 quantity in installation 1. Holding cost is H1. And then you have X2 in, okay, and then you have, where are we? Okay, H2 is here, and X2 is, this is the traditional amount that you charge. Is there any problem with this? Okay, am I missing something? Did I make a mistake? Yes.
I don't understand why we defined echelon holding cost as H2 minus H1.
It should be H1 minus H2. Okay. Okay. Is that now okay? Is this what you were asking? No, you were asking something else, I suppose. Okay. Let me.
The total with h2 in this case, I think.
Okay. Yeah.
Now it's okay.
Okay, you're right. Okay. I thought that you didn't understand this part, so you're right, actually. Like I mixed the different parts up. So the main reason of doing this, as we are going to see later, will be we are going to make sure that installation 2 makes decisions using system stack. Installation 1 makes decision only looking at the local stack. Okay? Oh, okay, this is x1. Okay, I think I confused everything. This should be x2, this should be x1, and this is going to be x1. Okay, now we're set. Okay?
And H1 below echelon stock of 2 should be H2.
Where?
Echelon stock of 2 yazıyor ya hocam. Onun hemen altında
Okay.
H1 yazıyor. O 2 olacak.
Okay. No, echelon stock of H of 2, this is the echelon stock. It's not the carrying cost. It's the echelon stock. Echelon stock of 2 is the sum in the system. So we don't have the H2. H2 was written probably for some other purposes. Sorry for the mix-up. But I think it is now clear, probably. So what we are doing is we are charging it in a little bit different way. Remember well, some of you may have taken the cost accounting. You are charging it in different ways. Now we are going to see why this is useful, because in this way we are differentiating between what's happening in the system versus what's happening in a certain echelon. Okay? Now I probably am going to give homework on Thursday, which is going to work on this echelon stock idea. Okay, I think that might be a good idea to give a homework. Okay, and I will solve it myself as well, so that I will clear up my mess as well. Okay, now, given this, note that anything that we do is not going to be very much different even if we use the concept of echelon stock. Okay, now let's work on the multi-echelon problem. Okay, now the first thing that we're going to do is we are going to model the installation number 1, okay, or echelon 1. So this is sort of the one which is right over here. Okay, so let's see what we are going to do. Again, for this simple example, remember the lead times and so on. So I can write Cn as x1, w1. Remember, lead time was 2. That's the reason why I only have 1 w. Okay? So I'm going to have this one. And this is equal to what? This is equal to L of x1. Okay, holding and shortage cost that I pay when I start with x1. Then I'm going to have alpha, which is going to be similar to the term that I have before. So this is the holding and shortage cost that I'm going to have next period, because I still cannot control it. And then I'm going to have f sub n of x1 plus w1. And we know that f sub n of u is equal to minimum over all y greater than or equal to u. And then I will have C1 y minus u, where C1 is the purchasing function for installation 1, purchasing cost. And then I'm going to have alpha square, y square now, because I know that only this term is not controllable, but this is the first term which is controllable. So I'm going to have 2 integrals from 0 to infinity, and I am simply going to have L minus y t1, t2, phi of t1, phi of t2, dt1, dt2. And then I am going to have plus alpha 0 to infinity of fn minus 1, y minus t, phi of t, dt. So this is going to be my problem that I solve in installation 1. Again, what is this problem? I already have x1. I know that w1 is on the way. And using what we learned from the single installation problem, I can write this in this form. Note that this first part is the uncontrollable part. I cannot control over this. This is the only thing that I can control. And this is the function that I minimize. This is what we wrote at the end of the last, in the beginning of this period. No, at the end of the last lecture. Okay? And so this is the only one that I can control. And I am going to minimize over all y's. Now, given this problem, given the fact that we have a linear purchasing cost, then the optimal solution for this case is governed by the xn bar, which is the minimizing point. Now, the interesting thing is that here in this problem environment, our order may not arrive. In other words, the stock may not be available in the second installation. So our order may not arrive, we know that. But still, the optimal decision structure is not going to change. You will try your best. You are going to give the order in the best possible way. If it comes, that's okay. If it doesn't come, then you are going to incur some additional costs. In other words, knowing that the second installation doesn't have that quantity is not going to change your optimal cost, optimal way of ordering. Okay? Because when you look at everything from installation 1, this is going to be the result. So you are going to order x sub n. Now, x sub n bar. Now, what will happen in reality is that if it doesn't arrive, if it's not available, okay, you are going to suffer because you are going to pay more costs. So let us see what will happen in that case. So this is sort of the interesting part. And I will try to finish this and then stop. Now, if xn bar is the optimal solution, what will be the optimal cost? The optimal expected cost would be C1, okay, x bar n minus u. Okay, I am simply putting x n bar into the equation, plus alpha square. So I have two integrals. And then I'm going to have L of x n bar minus t1 minus t2, phi of t1, phi of t2, dt1, dt2. And then I'm going to have alpha from 0 to infinity of fn minus 1, xn bar minus t, phi of t dt. So this is going to be the cost if it is available. Of course, this is only true if xn bar minus u is supplied. Now, what happens if only x2 minus u is supplied? Now, by the way, don't forget this xn bar is an order up to level. So the quantity that you actually order is this difference. Okay? So instead of having a value of xn bar, if we had x2 available in the second installation in general, not the optimal one, but the quantity which is available in installation 2 is x2, which means that total system stock is x2. Okay? If that was the case, what would be the cost that we would pay? We would pay C1 x2 minus u plus alpha squared. So I have exactly the same thing, but now instead of xm bar, I have x2. This would be the cost that I would incur. And what is x2? x2 is actually always, now note that x2 can be equal to xn bar, then this is going to be the optimal cost. But if x2 is less than xn bar, then this cost is going to be more than the optimal one. Okay? So let's call this equation 8, and let's call this equation 9. Okay? These are the equation numbers in the text. So equation 8 is the optimal cost. Equation 9 is the cost which is going to be realized. Now, if x2 is less than xn bar, in other words, the total amount available is less than what we want, then the difference between 9 minus 8 will be the additional cost of not having sufficient stocks at installation 2. In other words, you ordered, you want that quantity, you cannot receive. This is going to be the difference that you are going to pay because you don't have it up in level 2. And when we look at this function, 9 minus 8, which is equation 10 in the text, okay, it is interesting to see that it's a function of xn bar, and it's a function of x2. And what is x2? x2 is total system inventory. Okay? Echelon inventory, actually. Okay? Now you can see why we use this type of a notation, because this means that if total system stock is not sufficient, then we are going to incur an additional cost. Now, using this, on Thursday, we are going to wrap up the paper. This is one of the key parts that we should understand, and I will try to, I will start from this point on next time. Any questions? Sorry for messing up ones and twos, okay? It's a very simple concept, but I think I messed it up a little bit. So we'll make it up with the homework. Okay, questions? Okay, I'll see you on Thursday.